right, so we are doing lecture 4, exercise 4A, which is all about type classes and a few extra data structures such as map and array. So if you want to follow along with the course material, I recommend reading chapter 4. As before, I'm doing this in a slightly weird way. I am going to live stream at least some of the problem set as I do it here in Emacs. However, I don't want to spoil the problem sets for people who are taking the course. I'm basically making the bet that anyone taking the course, the chances that they are awake right now and paying attention to my stream are 0. So I'm just not worried that they're going to copy the material. And then once I'm done with all this, I will take this live stream and make it private so that no one can see it. And I will then edit it so that I'm only sharing the exercises that turned out to be interesting. If you're one of the hardcore people who really want to watch me struggle through these from the very beginning, well, God bless, and thank you for joining me here early on this Saturday morning, U.S. Eastern Time. So exercise 4A, we're going to be working with type classes. We've got a few type classes we're going to need. Notably, are things equal? Are things in a given order? Are things numbers? And are they fractional? I am assuming that I'm not allowed to add my own imports here. The function middle that returns the middle value, not the smallest or largest. And it should work on all types in the ORD class. Give it a suitable type signature. All right, this is the first type signature we will be writing in this set. So how do we do a type signature? I think we do it that way, and then the little double arrow, and it takes 3 arguments. So A, and it returns a 4th argument. Interesting choice to not have this be a list. I like it. Not the smallest or the largest. Okay, so we could do a bunch of comparisons here. We could use min and max, right? Weren't those take 2 arguments. And we've got compare. And none of these take 3 arguments. So whatever our solution is, we're going to be doing multiple comparisons. My instinct is to just guard this, pattern matching guard. So let's try that. Let's say we only wanted to solve this for x. We only want to return x if x is less than z or y and greater than z or y. Let's just write it that way. So if x is less than y and x is less than z. No, that can't be right. And x is greater than y or x is greater than z. Then x, else. And then we could literally do this for the other 2 the same way. Feels terrible. I'm going to be honest. Feels awful. Like that can't be the answer. Sisters of Mercy 667 says, you should play some Rocky's Boots on live stream. That would be fun. I have played Rocky's Boots. I have a video about Rocky's Boots. It is indeed on my channel. I did not do it on a live stream. It would be fun. Rocky's Boots is a lot of like moving things 1 pixel at a time. And the kind of Apple II UI. So I don't know that it would be fun. All right, can we do this with guards? Now that we've done this, Maybe the simplest thing to do is to simply encode this in a guard. So if x is less than y, or x is less than z, and x is greater than y, I hate this. I feel stupid for doing this. This is awful. But I don't want. I feel like I'm rat holing on this. So. Fail. Okay, good. I'm glad to have this fail. Let's look at this. Middle, 5, 6, 7. Expected 6 was 5. All right, hopefully I have done something wrong. So 5, 6, 7. 5 would be less than 6, and 5 would not be greater than 6 or 7. Therefore, it would not be x. We would fail this test. What did it say that 5 is less than 6, or 5 is less than 7? Both of those are true. I think we fell into the otherwise. Here's what I think. 5 is greater than 6, that's false. 5 is greater than 7, that's false. So it should not be falling in there. So 7 is less than x. No, the one that should be returning true is this middle one. So 6 is less than 5, that's false, or 6 is less than 7, that's true. And there's our problem. Literally, the definition of why writing functions this way stinks. So literally just a typo that got us. All right, exercise 6. Increment the function. Implement the function increment key that takes a list of key value pairs and adds 1 to all the values that have the given key. So this is almost like a hash function, kind of. You'll need to add class constraints to the type of increment key to make the function work. The function needs to be generic and handle all compatible types. All right, so we need a class constraint. That class constraint has to be that the value is numeric, but that's not a constraint we need for the key. However, I think in order to use a map, if I'm not mistaken, the keys need to be orderable. That's what I think the class constraint needs to be. And let's see if that compiles. Good, it still compiles. I was looking at data map earlier today, and I remember that comment that that the keys have to implement ORD sticking out. So what this is an insert or a replace. Adds 1 to all the values that have the given key. True. So this is super interesting, right? This is saying that there can be multiple keys. So maybe this is not a map. Can I have multiple keys in a map? More data structures, key value pairs. Insert a value into a map, overrides any previous value with the same key, returns a new map. Right, so this data structure is not possible with a map if I'm with a Haskell data map, if I'm reading correctly. Because if true is the key, then we can't have a value that has more than that. We could use an array. Or we could just use a list. All right? And in fact, that's what this is using. One ambiguity here is what happens if there are no values in our existing data structure that have that key. Would that be an insert? No. Would you do it from, would you implicitly, if you did true and you only had a false in this list, would you suddenly have true, 1? I don't think so. They don't say that this is an insert. This is strictly a replacement. Okay. So what are our arguments here? Our arguments are the key and our list. All right. So again, this feels like a folder to me. I love folder. And then we have an accumulator, which is going to be the results. And we're passing in KV list, which of course we could get rid of that later and return this in. But this is going to be what? This is going to be a key and a value. And in fact, in doing this, if you recall, I was struggling back here because I was like, oh, but what if it's nil? And then what if the accumulator is nil? And I completely, well, that's neither here nor there. Let me not get confused by that. So we're going to get an old key and an old value. And no matter what, right? Let's do a case again. Odd of. So there's two cases. There's EQ and there's everything else. And in the case where it's everything else, that means the keys are not the same. And so all we're going to return in that case is this glommed onto the accumulator. So really this is our only tricky case. So if old key and old value match, we're going to return old key, doesn't matter which one. Old val plus 1, glommed onto the accumulator. How did I end up with an extra? I feel like I have one parenthesis too many here. Yeah. Okay, and that goes there. Nil KV list. Let's see if that compiles. No, it doesn't. Okay. Couldn't match expected type, list of keys and values, with actual type, a pair. Okay, so I did something terrible here. In this expression. Oh, again, it's just parenthesization. Hungry Joe Warren on the chat says this could be done in terms of map rather than folder. You are correct. And I bet the map implementation is much simpler. I don't know why I like folder so much, but you're absolutely right. And map is probably an easier way to do this. Let's do this. Get rid of that. We'll make it point free. And that passes as well. Well, what would the map implementation look like? And it passes the test too. So there you go. 2 implementations, one using folder, one using map. And in fact, in this chapter, the instructors do talk about the fact that map and folder, are essentially interchangeable in certain ways, or rather, that you could use folder to implement map. Thanks, Hungry Joe Warren. That was a good suggestion. Exercise 8. Mr. Anderson. Exercise 8. Given a map from player name to score and 2 players, return the name of the player with more points. Okay. If the players are tied, return the name of the first player. Ooh, okay. If player doesn't exist in the map, you can assume they have 0 points. Wonderful. Hint, map find with default can make this simpler. And then they give us some examples. So as I said earlier, I have not done a lot with maps. So this is going to be interesting. So how can I write this if I don't know anything about maps? Well, I could go read the documentation, but who wants to do that? Can I write this with holes such that I'm isolating the actual calls to map in my holes so that I don't have to think about them until the very end? Let's do this with guards. Scores is our map. Player 1 is the name of the first player, and player 2 is the name of the second player. So what we want to do is that if player 1's score is equal to player 2's score, then we want to return the name of the first player, which is that. If player 1's score is greater than player 2's score, in fact, that just tells us right there, if player 1's score is greater than or equal to player 1's score, we want to return player 1's score. Otherwise, we don't even need to do anything else. We're going to return player 2. Where, pretend I could spell, P1 score equals something, and P2 score equals something else. So at this point, I gotta actually get those scores out of the map. So at this point, I need to look up the documentation. Let's see, they said find with default. Let's go look. Guess we have to import it. Type find with default. So given some ordered keys, we have, that's probably our default. That's our key. That's our map, and that's our result. See, what feature is Haskell missing? Named parameters. Like, I get that we all want to cosplay as mathematicians, but like, if you had named parameters, this would be even more self-documenting. There is no lie. The greatest lie the devil ever told was that he didn't exist. The second greatest lie the devil ever told is that a type signature is adequate documentation. It is not. A type signature is not documentation. It's a type signature. And except in the most trivial cases, it's not enough. But let's try and do this. Find with default. I think I said it was 0. Then the key. The key is the name of the player. And then the map, which is scores. That's what I think the answer is. Let's see if that compiles. It does, good. Let's run the tests. Passes the test. Hungry Joe Warren says, agree with that, meaning type signatures are not documentation in general, but I do think that type signature is adequate documentation in the case of map find with default. Yeah, I'd agree with that too. We were able to figure it out without too much difficulty. But it becomes an article of faith. It becomes something people say, I think because it works in the trivial cases. And you very rapidly, if you're writing code of any magnitude, get out of the trivial cases. And exercise 10 has to do with map, data.map. And exercises 11 and 12 have to do with data.array. So I read the documentation for these carefully, and I think we're ready to do them. So, exercise 10, we're writing a function that transfers money from one account to another. But there are a number of conditions under which we shouldn't perform the transfer if either the from or the to account doesn't exist, or the money is somehow not right. Either we're trying to transfer negative dollars. I'm assuming they're dollars. I'm American, sorry. Or the account doesn't have enough money. There are many ways to implement this logic. We got map member and map not member. Okay. Well, the thing that jumps out at me is there are at least these 4 situations where we don't do anything. And the don't do anything case should be simple. It should just be return the map as it exists. So we look at their examples. We define this bank, which is a map with Bob and Mike 150. And then these 3 examples are all examples of examples of invalid situations where one should not do the transfer. In this one, we're trying to transfer more money than Bob has, and we're just returning the original map. And the same is true here. Any transaction involving Lisa's not in the map, we're just returning the original map. So that feels very tractable for some sort of guard situation. So we're going to have 4 conditions. We could do this 2 ways by De Morgan's law. We could either have 4 conditions, and if they're all true, we do the transfer. Or we could have 4 conditions, and if any of them are true, we don't do the transfer. I have a vague preference, for no particular good reason, for the former, to have 4 conjunctions. Because then I know that we're not going to fall into the move money case if there's some 5th condition that we haven't thought of. So let's try that. So what are our conditions again? If the sum is negative is the most trivial condition. We have this amount. That's the amount we're moving. So we're saying amount has to be greater than 0. Okay. And then we're not going to be doing multiple guards here because these aren't separate cases. This is all one case. So let's do it this way. What's another case here? If the account doesn't have enough money, we're handling one thing. Of course, to figure out how much money is in the account, we have to figure out how to query this data structure. So for right now, let's, if amount is greater than the amount available, and we'll figure out what available is later. Then we have if the from account doesn't exist and the to account doesn't exist. And that is a situation where we need to query this map. And we have this map member operation, which I did look up. In fact, let me show you. Do this. Now type. Data map member. K is our key, M is our map, and we're getting back a true and false. So that's nice. That's a very simple API. Map member, our key. Our keys are named from and to. And we have a similar thing for that. And so if all 4 of those are true, then we're going to do something. Otherwise, we're just going to return the map as it existed when we were called. So we have 2 holes here. One hole is to actually do the moving around, and the other hole is to look up the value for one of these things. So let's take a look. There is a function called lookup. That takes a key and a map, and it returns a maybe. So whatever we get back, what did I say? It said a key, and the key is going to be the from account. We don't care about the to account here, right? And so what we're going to get back from here is either a nothing or a just. So this is a good place for case analysis. And if we get back nothing, then there's no money available, right? Because they don't have an account, there's no money available. Or we're going to get back some just value, and we'll just pull that out of the optional. So I think that's right. So we can do some testing here. Actually, I've never shown you this. If you have not seen it, a very convenient. So if we leave our hole here and we try and compile this, why did I do that? If we leave our hole here and we try and compile it, we will get the type error that we asked for. Right? Here's our hole. That's telling us a bunch of stuff. It gives us all the hole fits, etc. But we can do something else. Something that I think is very interesting. instead of saying putting a hole, let's put the keyword undefined. And you see it compiles. Now, as implemented, this is a partial function. So if we run any test that hits this code, we will have a runtime exception. So you've heard me rant about how much I hate partial functions. Why do I like this? Well, because in a situation like this, where I've got a bunch of conditions and I want to make sure they fall into the part of the function I've written that I've completed, this allows us, copied the wrong one there. This allows us to test that code. And here we're finding out that apparently I haven't written this correctly, because this should not be falling into that undefined error. Bob Mike 120 Bank. Maybe I'm wrong. Maybe I can't use undefined this way. I thought I could. Oh well. Let's go back to actually filling this in. So what do we have to do in this case? Oh, this actually found us a bug. This is a real bug. The reason we're hitting this undefined is that I wrote this check exactly backwards. I said if amount is greater than the amount that's available, when really this needs to be less than or equal to what's available. And so if we've done that, is this still defined? No, I have to actually define it again. If we've done that, now I could actually test it and it works. And let's test these other cases. I didn't think I had made that mistake. So as long as we're testing, that works. And I don't think I tested this one yet. And that works. And our success case, we know will fail. Well, let's test it. We expect this to fail with a runtime error. Good. All right. So now we have to actually write the rest of our function, which is here. So there are 3 to 5 I think I want browse. There's a bunch of ways to update a map. In particular, we've got alter, which we already use. We've got alter F, which is somehow the functorial version of that. We have adjust with key, and then there's update as well. And I'm going to be honest, I stared at the data value lazy Google page for this data map lazy for quite a while, and trying to kind of like understand the subtleties between these. Let me get this on screen. And it wasn't quite clear to me from the documentation what the benefit of using one of these versus the other is. So I'm just going to go with adjust. So looking at the type of adjust, let's look at it in our GHCI. What have we got? We've got some function from A to A. All right. We've got our key and we've got our map, and we're going to get back a map. So that seemed like the simplest variant of this to me. So what do we got to do? Well, we have to take some money out of the from bank account, and we have to put some money in the to bank account. And we know if we get here that we can do both of those operations. So it's just map, because I imported it qualified. We've got map adjust. We have the operation, right? So let's do the to case, because that's very straightforward. And that should be an A to A function. In fact, we can check it, right? A to A, so that'll fit. And then we need the key, and then we need the map. So this, if we just did this, would increment the 2, but would not decrement the from. So we can build this backwards. You could do this in either order, but you know. And then we can plus negative amount. I learned my lesson, I think, from that subtraction is not commutative, so use addition when you can. And here we don't need to provide the bank because we're actually providing it here. So with the standard disclaimer that I'm probably messing up parentheses somehow, let's see if that compiles. It does not. Because I'm applying it to too few arguments. So this is a great sample Haskell error message. It's a good error message that giving me a lot of extraneous information that doesn't actually tell me where the error is. Like, first of all, we end up with this crazy type, which is not what I intended, of course. And second of all, it's telling me the wrong place. The thing I'm actually missing here is right here, in before this $sign. But reading this, you would say, oh, well, it's something to do with this right here. I never said where to take the money from. So a criticism people have made of me, which I think is, fair. I'm not going to deny it. I need to get it. There we go. Is that I use too many parentheses. And this is a case where I feel like if instead of using that, I'd done that. To me, even though the parentheses make it a little hard to read, I feel like it's more readable. And that indeed compiles. So let's test it once more time with our success case. And transfer Bob, Mike, 20. Right? Bob is 80. Mike is 70. That 50 plus 20 is 70. So that's all good. Set for a test. I remembered the test this time. And we have passed exercise 10. Given an array, find the index of the largest element. You can assume the array isn't empty. You may assume that the largest element is unique. Hint, check out data array indices or data array socks. All right, let's check out indices. I actually already looked at this, and I think it's going to work. Type data array indices. So, given some array, this returns a list. And we already have a list function, and in fact, at the top of this test file of these exercises, they give us a hint. And that's a pretty direct hint to this. Because the type of maximum, which I always confuse with max, right? Max operates on a pair and returns one value. Maximum operates on anything foldable, which includes a list, and returns the maximum. This is some really top tier Haskell naming here. Geez, guys, come on. This is namespaces exist. You could use them. They're almost free. So this is going to be get the list of indexes. I think it's just that. Set for a test.hs. Okay, that doesn't work. And it doesn't work because I think I named it. My brain, man. My brain is something else. Okay, good. What do we got here? Max array, max index, false, true. Expected false was true. Given an array, find the index of the largest element. Oh, I did misread it. I thought they were saying the largest index. And I have implemented the thing that gives you back the largest index. But that's not what they want. Right? I gave back 54. But in this case, they want the largest element, which is going to be 53, because 53 contains 20, and 20 is larger than 19. All right. Yeah, hey, I like it when I make a mistake like that. That's not bad. All right, so first, we're going to get that associative array, right? And I'm going to use let syntax because I don't like it. Then we want to unzip it, right? So instead of calling this R list, let's call them index list and val list. And we're going to unzip it. So now we have these two lists. Max val is going to be maximum in valve list. Maximum in val list, right? I think that's correct. And now that we have that maximum, we want the index. And to be clear, this is the index into the array list or into the val list, not the index in the array, which could be completely different. So max index is going to be lm index of max val and val list. And we are told that we can assume it's unique. So this should be a safe operation. And this is going to give back a maybe. So to be perfectly safe, we would want to case this. I'm going to risk writing a partial function here, specifically because we were told that it's unique. And we know that it must be there because we literally just got that back. So I'm cutting a corner here. Probably not something I would write in production code. And now that we have that max index, we can do index list that returns a maybe also, but again, I'm destructuring it because we should be guaranteed if this doesn't return a just, then this failed in some catastrophic way that should not be possible. So that's how I'm justifying to myself writing what is effectively a partial function here. And if I redid this, I'm sure I could restructure this so that it was legitimately a total function, but I think it should be okay. Did we import data list? Can I do this? I've never referred to an operator this way. Data list does not export that. Okay. All right, I'm going to use the unsafe version. And the unsafe version, why am I using the unsafe version? I'm going to be honest with you. It's because this is taking a long time and I want to be done. And I'm reasonably sure the invariants here are going to protect me. Okay, couldn't match expected type int with actual type I. We don't know that the array, meaning the actual, this array, we don't know that that type I is of type I, but we know that this has indices this should work because, oh, what the heck am I doing here? Yes, that was it. Literally typed the wrong thing. All right, what can we do here? There's no examples given. Let's go ahead and run the tests. And I did it. On the very last test, I made that mistake again. All right, we have finished set 4A, but if I'm honest, this sucks. Like, this is bad. I'd fail me if I submitted this as a solution to this problem. So maybe this is a good one to put on the edited version of this stream, on the edited version of this video, because I know I'm not helping any student. If you're a student in this class and you submit this as your solution to this problem, you deserve a bad grade. So we have two choices here. Choice number one is I could redo this exercise and do it in a more total, more organized, better way. Choice number two is you can do it and you can put your solution to max index in the comments. Or if you're in the class, you could share your solution. But I kind of like this. I like the idea that I've given you a solution that's garbage. Technically meets the requirements of the tests, but man, this is not good. And then, we'll leave it as an exercise for you. Why is this garbage? Why am I having this reaction to this kind of tinker toy Haskell I've written? And what would be better? I think that's a good question to think about. So let's leave it at that. This has been Set 4A. If you're watching live, congratulations. You are one of the few, the proud, the very dedicated Tea Leaves viewers. The live version will be live for subscribers, all 5 or 6 of you. If you do subscribe to the channel, you get to see things like this more often. You get notifications when I do live streams. If you do not subscribe, this will be going live probably in about 3 weeks. I think set 2 just went live. Set 3A is next week, 3B after that, and then 4A, just in time for Thanksgiving. So you've been watching Tea Leaves Programming. We're programming like it's 1979. You're watching Haskell for Dilettantes. Thanks for watching.